Hi, my name is Michael Pelletier, and I'd like to take a few minutes to describe the GraphBLAS API and how to use it in Python with the PyGraphBLAS library. I'll talk about what it is and how it works, and give a quick demo of how to use it to solve graph problems in Python using linear algebra. Before I get to Python, let's take a moment to talk about what the GraphBLAS is. It's an API that defines sparse matrix and vector operations. It focuses on the idea that a matrix can be represented as a graph. Here we see a graph represented two different ways. On the left is the commonly used representation using nodes and edges, and on the right is a representation of the same graph using a matrix. For example, look at node 4. It connects to 1 and 3. In the matrix, you can see there's a value present at the intersection of the row 4 with columns 1 and 3. These represent two directed edges, from 4 to 1 and 3. Both representations contain the same information. The left is more intuitively understood by a human, and the right is kind of hard to picture. So how is a matrix more useful for programmers? The answer is linear algebra, and we'll get to that in a minute. But first, notice how the matrix is sparse. There are more missing values than present, and the values are spread out pretty consistently. They're not just crammed into one corner. This sparsity is a pretty general feature of many graphs, no matter how you try and store them in memory. Of course, you can have a graph that's fully connected, and then the matrix would be dense. But that's not, for example, what a social or computer network looks like. Everyone on Earth doesn't know each other, and every computer on Earth doesn't have a direct physical connection to every other. Globally speaking, both of those types of networks are very sparse. And this is one reason why graph representations are not commonly used with dense matrix libraries like BLAS or NumPy, because there would be so much wasted space. Only small graphs could fit into memory, and CPU caches would be worthless because the data is so randomly distributed. This is why GraphBLAS provides sparse matrix types. Sparse matrices use clever tricks to store and operate on only the values in a matrix that are present. Unstored values can be interpreted as a default value like 0 or false or even positive infinity. Depending on what GraphBLAS implementation you're using, the storage and operation on your graphs might happen on a CPU or GPU, or more than one of either or both. As a user, you don't have to worry about the most optimal sparse matrix algorithm for your hardware. The GraphBLAS implementers have solved that problem for you. So as I mentioned, the advantage of the matrix representation of a graph is linear algebra, and the core operation of linear algebra is matrix multiplication. It turns out that matrix multiplication takes a single step in a breadth-first search across a graph. For example, here we see the same graph. We multiply the graph by a column vector with a value present at 4. The matrix and this vector are the input, and the output is a vector containing the nodes 1 and 3, the nodes connecting in from 4. So you start with a matrix that defines the graph and a vector that says where you want to start. And the result of matrix multiplication is a vector saying where you've ended up. It takes one step across the graph, so you can probably intuitively see how you can traverse the entire graph by looping over this multiplication operation and accumulating information as you go. We'll get to that shortly. This example is very simple on purpose to explain the concept, but the input doesn't have to be a matrix times a vector with one set value. The vector could contain many set values, and the result would be the combined neighbors of all the nodes. The input can also be two matrices. For example, if this graph were a social network, a useful operation would be to find the friends of each user. This is a very common graph problem. To find the friends of this graph, using GraphBLAS and linear algebra, all you have to do is multiply it by itself. The friend of a friend matrix is literally the friend matrix squared. The result will have a row representing every user, and the values present at the intersections of those rows will be the columns of the friends of that row's friends. So linear algebra as a way to traverse graphs with matrix multiplication is clearly a powerful idea. GraphBLAS takes that idea further by using mathematical objects called semirings. Semirings are ways to substitute different operations into a matrix multiplication in order to achieve different transformations. The kind of matrix multiplication commonly learned in school is where the inner operation is to take every row element by position in A and multiply it by every corresponding position in the column in B, and the outer operation is to sum the results of those multiplications. If you're not familiar with that, you might want to stop here and watch any number of great matrix multiplication videos on YouTube. I personally recommend 3 Blue 1 Brown's Essence of Linear Algebra series. Those operations taught in school are actually one of many semirings, which for classical matrix multiplication we'll call plus times. This is the matrix multiplication you're already familiar with. But let's say instead of those operations, we substitute 2 other binary operators. For example, instead of multiplying, we add, and instead of adding, we take the minimum. For example, here's a graph that represents, let's say, cities and distances between them. What's the length of the shortest path from A to C? The process is pretty simple. We add up all the lengths of all the paths and then take the minimum. But this is the same data access pattern as matrix multiplication. But the inner operation adds instead of multiplies, and the outer operation minimizes instead of adds. This is a different semiring called min plus instead of plus times. And in math circles, it's sometimes called a tropical semiring. It's still matrix multiplication. We've just substituted different binary operators into the process. Instead of multiplying, we're adding. Instead of adding, we're taking the minimum. As you can imagine, there are many different combinations of binary functions. GraphBLAS comes with something like 960 predefined semirings. You can even define your own semirings that work on your own custom matrix element types. So here's an example of the shortest path problem in Python. This function takes a graph and a starting node and returns a vector with the distance from that node to every other node. The algorithm is straightforward. The code creates a result vector v and sets the starting node distance to 0. Then it loops over every row in the matrix, which is every node in the graph, and it multiplies the vector by the matrix using the min plus semiring. After enough iterations of the loop, either every node has been checked or every distance will be known and further multiplication won't change the result, and the loop will terminate. An area of active research for GraphBLAS is deep neural networks. One of this year's graphchallenge.org problems for the 2019 High Performance Extreme Computing Conference was computing forward inference with a deep neural network, which is a sparse graph. Here, I'm showing a slide deck from the challenge showing an example of the sort of network used. The network classifies images of handwritten numbers, the MNIST dataset. And the challenge problem is to use sparse graphs to do the forward inference process of showing the network an image on the left and classifying the result, which comes out on the right. The challenge organizers already trained the model and provided the neural layers and weights, and the challenger's task was to take that data and come up with an efficient classifier for a range of image sizes and layer depths, shown here in this next slide. Here we can see 3 different depths of layers and 4 different layer sizes. The problem obviously gets harder the further along either of these dimensions you go, and you can see the total edge case for the largest 1920 by 65,536 example is 4 billion edges, and the smallest case of a 120 layers by 1024 neurons is 4 million edges. So going back here, we can see at the bottom the math equation that defines the challenge. Y and W are both matrices, and B is a vector. H is an activation function called ReLU. Let's scroll down a little here so you can see the equation. So clearly, this is a problem defined in linear algebra. No one was required to use GraphBLAS in this challenge, by the way, but you can see how natural a fit it is. So the task of translating this equation into GraphBLAS is actually pretty straightforward. You start with an input image that is a matrix, and note this matrix is not a graph. Every row in the matrix is a character image unrolled, spread out into a single row. so each element represents pixel values, not nodes in a graph. And you transform that matrix step by step through the layers using matrix multiplication against weight matrices that do represent neural connection graphs from one layer to the next. And the final output is a matrix which reduces down to the categorization of the images. This is so easy to do in GraphBLAS that one of the challenge champions from this year, Dr. Tim Davis from Texas A&M University, who's also the author of the Sweet Sparse GraphBLAS implementation, entitled his paper, Write Quick, Run Fast, Sparse Deep Neural Networks in 20 Minutes of Development Time via Sweet Sparse GraphBLAS. Well, it took me longer than 20 minutes, but here's the same function that Tim wrote, but translated into Python. And we'll go through this line by line to show how elegantly it maps to the mathematical equation I showed on the last slide. First, note there are three inputs: a sequence of neural layers called layers, a sequence of biases called biases, and a matrix of input features called Y. This is the matrix that contains an image per row. The core of the function is this for loop. Starting with the initial input, the loop moves through the layers from left to right, multiplying the input by the weights of the current layer, and then adding the bias, and computing the ReLU function. Note that the bias addition is still a matrix multiplication operation, but it's using a plus-plus semiring, which makes the transformation add the biases instead of multiplying them like a plus times semiring used for the weights above. This also shows how the default semiring is just good old plus times, so you can still use GraphBLAS to do typical matrix stuff. You would use, say, NumPy for, especially if your data is sparse, or a combination of sparse and dense data like this example. For the final step at the bottom, you can see the ReLU function. It basically says, find everything in y greater than 0 and slice it out of y, essentially throwing away entries less than or equal to 0. The second step of the ReLU is in a sense to truncate values greater than 32. That line takes everything out of y that's greater than 32 and assigns it to a matrix M. If there are any elements in M, meaning its length is non-zero, then use M to do what's called a masked assignment, assigning 32 to those elements in y that are greater than 32. And that's the H function in the equation. You loop and repeat until there are no more layers, and you're done. So this slide shows some recent benchmarks I did with the Deep Neural Network Graph Challenge data on an AWS Spot instance with 72 cores and 192 gigs of RAM. The numbers shown here are time in seconds. It's hard to know what these numbers mean in isolation, but they're in line with the performance that Dr. Davis got with both his C version and MATLAB code versions using GraphBLAS. It's not a true apples-to-apples comparison because I was using a cloud server with 72 threads and he was using an NVIDIA bare metal compute server with 40 threads and more RAM. So there's going to be some more tuning and testing, and hopefully soon we'll be able to run all three languages, C, MATLAB, and Python, side by side. And we're pretty confident so far that they'll all be very comparable. But you can see all the way on the left, the very smallest cases took just a little over of a second. And all the way on the right, the biggest case, almost 2,000 layers of 65,000 neurons each, which is the 4 billion edges, took a little over 30 minutes. Proportionally speaking, these numbers look really good. Another interesting side effect of using the GraphBLAS is that the case all the way on the left, I can run on my Chromebook while I'm doing testing. The case all the way on the right, I can run on a very large server, but it's still the same function written exactly the same way. So I want to ask a few questions about the future. In the short term, sure, we'll see more GraphBLAS adoption and more high-level languages taking advantage of it. But I want to look out a little longer term here. Physicists and mechanical engineers have long used linear algebra to express the evolution of complex systems. As programmers, though, even in the big data space, we seem a bit stuck in this low-level paradigm of hand manipulating every bit of data in procedural code. But what if you could envision your problem globally as a series of linear transformations expressed in a simple language? Food for thought next time you're staring at a complex ETL pipeline. And finally, this picture is of a recently developed processor by Cerebras. I have nothing to do with this company, by the way. I just saw this posted recently to the GraphBLAS forum. 46,000 square millimeters, 400,000 cores. This is on a 16 nanometer process, so there's still a lot of downward scaling to be done. In a few years, maybe they or someone else will have 1 million cores. At this scale, the procedural ways we have to express graph problems become very, very tricky. But if GraphBLAS were to be implemented on this hardware, you could run your programs portably and optimally with no changes. If you'd like to explore the science of the GraphBLAS more deeply, you can't get a better source than Dr. Jeremy Kepner's book, The Mathematics of Big Data. Dr. Kepner is the founder of the Lincoln Laboratory Supercomputing Center and at the Massachusetts Institute of Technology, the biggest supercomputing center in New England. He's been researching these methods and is a central member of the GraphBLAS forum. His book is easy to read, but also dives deep into the mathematics of big data, and it's no surprise he has a lot to say about graphs, but also other big data structures. The book is also well illustrated, and I highly recommend it. MIT also has an open courseware given by Dr. Kepner called Signal Processing on Databases that works from the book and gives many code examples. So thanks for watching. I hope this gave you a good idea of what the GraphBLAS is and how to use it. Head on over to graphblas.org to find out more about it. If you want to try it with Python, go to my GitHub account, github.com/michaelp/pygraphblas. You can run pygraphblas if you have Docker installed, and it'll drop you right into an IPython interpreter where you can import it immediately and start playing with it. There's still a lot to do, including better test coverage and a Jupyter Notebook tutorial, so if you feel like contributing, I'm always happy to see issues and pull requests. You can also find my other GraphBLAS project that integrates GraphBLAS with PostgreSQL. This is not quite as useful yet as pyGraphBLAS because of the concurrent, transactional, and durable nature of Postgres. And what any one matrix is becomes a bit more complicated, and that's a talk for another day. Also, community member Gabor Snjarnias has a great resource on GitHub which contains all of the links you need to dive deeper into the subject, and you can see that here at the bottom. Finally, I'd like to thank Dr. Jeremy Kepner from MIT and Dr. Tim Davis from Texas A&M University, as well as Dr. Tim Mattson from Intel and Dr. Scott McMillan from Carnegie Mellon University for advising me over the past few months while working to expose Python and Postgres to the GraphBLAS API. Thank you.